Well, it's a pleasure to be here, and hello, good evening to all of you. Thank you for staying up so late. And we also have been experiencing this online lecturing, and I think it's actually a good idea. And so don't have to travel, and we can share our experience even sitting at home. And first of all, thank you, Alexei, for your invitation. And we want to follow up now on M.Graetzel's talk, who has very aptly described how the perovskites were discovered and who the persons were involved in this discovery. So, this is a group photo which I took when I visited in 2017, and we can see Andre on the right side, and Alexei here. I forgot the names of the other students. So anyway, that was a remarkable visit, and it kind of was the highlight of a collaboration that lasted for several years and was financed by the Swiss National Science Foundation and also the Russian Science Foundation. And here's just the outline of the organogram, how this collaboration was going on. It was very, very successful and ended in a joint publication in a Nature journal, which I will later show to you. And here's just a picture of our group discussion. The person on the right side is Professor Andre Chevelkov. I think he's the dean of the faculty. I'm not sure, but he's in a supervisory function. And so today the journey will take us from first of all, the inspiration we had. I mean, sometimes people ask me, how did you invent this or this? And inventions never come on their own. We have to have some inspiration, and usually we rely on our fathers of science, and we just follow up on some of the footsteps. And so, so this will take us from the inspiration. We pass through the mesoscopic solar cells. I should tell you that today's perovskite cells, the best ones are still mesoscopic. They use a mesoscopic junction. So the electron selective material is a mesoscopic oxide. And just a few days ago, there was a paper in Science on the first stable, the first perovskite cells that passed the very stringent heat damp test and also temperature cycling test. And that was from Australian university, and they still use. I was pleased to see that after 8 years of studies and I think 15,000 papers published on perovskites. This configuration which we pioneered is still being employed and is a forerunner still, although there are planar configurations now that compete and they have their own advantages. And so the perovskopic dye-sensitized cells, they are now in production, and I show you a few applications before we go to perovskites. And but then there was this evolution that there was a striking discovery made by Tomi Asaka, who used the quantum dots of perovskites to sensitize photoelectrochemical cells, dye-sensitized cells, just replacing the dye by these perovskite quantum dots. And here you see the perovskite covering these nanoparticles of the Ti2. And so, and that, first of all, that happened in 2009, and nothing happened after that for 2 years. These cells were very unstable, and only one scientist picked it up. That was Namgyu Park. And he published a paper in 2011 with this higher stability, used different electrolyte solvent, and higher efficiency. And it was Namgyo Park who contacted us to collaborate, because we had a solid state, developed a solid state system, and that's how the solid state version of the dye-sensitized cells were born. And so first of all, since a lot of young people always ask me, so what was your motivation and inspiration? And what was your research approach? How did you get to this discovery? And so, well, we were motivated clearly by the energy crisis. After the Yom Kippur War in the 70s, first crisis, we couldn't get the gasoline, and I was wondering. I was a postdoc in the US at that time. I was thinking, wow, I mean, if you can't get everyday gasoline, how much is there? And maybe one day it's all gone. And so, so that started me on this research, and you can see the stunning amount of energy one American family. It's actually 10 kilowatt. It's a power continuously 10 kilowatt per person. That's what the U.S. The U.S. inhabitants consume, and in Europe it's half. So, but imagine 10 kilowatts. I mean, to live, to just sustain your life, is only 100 watts. So it's 100 times more than what you need to survive on Earth. So this has to come down, of course. And you see, the Africans, they use 30 times less, okay, and the in India 20 times less. And so there was also this these continuous oil accidents, and shortly after this, well, not shortly, a few years after this explosion happened, I was in Cancun, Mexico, and I received a prize. And so the Zewail Prize, Molecular Science, very prestigious prize, and it was given at a conference there. So, so I thought, well, I might as well take a swim in the Gulf. When I came out of the water, I was full of tar. My whole body was. That was terrible. I had to go through a detarring station. Believe me, I didn't go back into this water again. And so there's also there's much more scary, the increase in temperature. And so we all know about climate change and the CO2 increase. So here's, I go often to Singapore, here's some pollution, and you know, these ladies are wearing something that we are very familiar now in Switzerland. We're supposed to wear those masks on all public transportation, okay? And so I always have my mask with me. And but this mask was against the pollution and not against the COVID disease. You see, everybody wears a mask here. And that was because there was a terrible day in Singapore with very high particle count. Yeah, and so our motivation really was to make a contribution to the quest for clean and renewable energy sources. And just to put it in a nutshell, if you want to know how things evolve the next 50 years and projections, well, there is on the internet, you find the so-called SKY scenario. That's analysis by Shell Corporation. And this particular analysis is groomed so that it meets the Paris Climate Agreement. In other words, maximum 2 degrees rise in temperature. And if you do that, then you come up with the PV. The PV has to kick in a lot. I mean, percentage-wise, but you see the whole cake also goes up higher. So it's a factor of 200. PV has to go up by a factor of 200 in installed capacity. And that means today we're at 500 gigawatts. So can imagine, I mean, you're talking about 100 terawatt peak installed capacity. That's average capacity installed. So yeah, so these are challenges, and we all have to, of course, help to manage that and start on it as soon as possible. And so what photosynthesis shows the way. See, photosynthesis is a molecular absorber, and it produces the stored power in chemical fuels, in sugar mainly, is 95 terawatts. So compare this to 18 terawatts our present consumption. So photosynthesis does better, much better still than what our total consumption is. And so that also induced us to work on molecular systems in the very beginning. And so that's, I won't say much about it, PSC, because it's a talk about PSC. But clearly the PSCs, the perovskite solar cells, emerged from the mesoscopic dye-sensitized solar cells. And so just to remind you, mesoscopic dye-sensitized solar cell uses a nanocrystalline film that is electron selective contact of TiO2 or tin oxide. And so the dye is sensitizing this film, electron injection from the excited state. And so that was the first three-dimensional junction that was used in photovoltaics. And it took a while to develop it. It took years. And finally, we had this Nature paper with Brian. And this has received 31,000 citations. So it's been very, very frequently cited. Why is that? Well, because it was a change of paradigm. Before we published that paper, people believed only in PN junctions as suitable devices for solar light harvesting. So silicon PN junctions and other materials, gallium arsenide. But to use this high surface area, this mesoscopic film that was totally out of the normal. And people first didn't believe in our findings, okay, but we could demonstrate. Here's a demonstration. And the person on the left is David Carr, he's from the Weizmann Institute. And on the right side, we have, I think there's Professor McQuillan. He's from Otago University in New Zealand. So the two made this cell. It looks like a tainted glass, but it's a PV cell. And you can see it turns a fan. We may not have seen it, but look at it carefully. You see that fan is turning on diffuse light. These are bifacial cells. They capture light from all angles, so they work very well in diffuse light. And so, yeah, so, oh, wait a minute, I'm going the wrong way. Wow. So this became a citation classic, okay. It's one of the 100 most ever published, most cited papers in science. And here's Brian and I were at a conference in Uppsala. So this evolved and applications evolved. And recently, also the diffuse light application became very prominent. And we were even able to beat gallium arsenide on a diffuse light application. And so, yeah, so this has led to some commercial applications. I just mentioned, there are many, but I mentioned Exeter for good reasons, because they are the leader now in the diffuse light, ambient light harvesting, it's called. This is their manufacturing plant in Stockholm, 3,000 square meter, next to the KTH. And King, the tape cutting ceremony, the King of Sweden, Adolf. And this is Giovanni Fini, this is the CEO, and Henrik is the CTO of the company. I skip over this, it's just some products. These are just self-powered devices. They capture so much energy from the ambient that you don't need a battery. Endless music, endless listening. So look at their website, you can get inspired, okay. And we had a big celebration when SoftBank invested, and they raised $70 million in the last year and have their now first products. Samsung is making a first product. And here we got the Rosnano Prize. And I think that somebody will recognize this person here. This Alexei. And this is the former Prime Minister of Russia, Shuvai. And this is the Fuvas, Dr. Fuvas from Exeter, because we both got the prize. And these is a nice looking lady on the right side. So, okay, now we're going to perovskite. Don't worry, don't get lost. So you already have heard the introduction that Professor Katz gave, and we have these special features of the perovskite. It's but I mean nothing really unusual except that they have a ionic and electronic conduction, and that was, by the way, contested until about 3 years ago. People who didn't want to believe that these were ionic conductors and electronic conductors. But they're ions. I mean, they're composed of ions, and so these ions can move. And so, yeah, these organic ones, actually, Dieter Weber from Stuttgart, he discovered this organic version. And so here's an example. And so, yeah. And so what is unusual about perovskites is the band structure. They have a valence band and conduction band. They're antibonding in nature. And what that tells you is if you break a bond, it doesn't produce a defect in the band gap, okay? Because breaking a bond stabilizes the system. It's a little bit weird to say that, but since these bonds are antibonding, then so that's a special feature about these materials, and it helps to avoid defects. The defect, even with solution process films, you have low defect levels. And so here is what, how the very beginning, I already mentioned to you that we had this, the dye-sensitized cells with the perovskite. Here you see the nanoparticles of perovskite, these black dots. That was the very beginning on the same mesoscopic films we had developed for the DSC. And yeah, and then came the solid state version, and what was used was a configuration that we had published in Nature in 1998. It was a solid state version with spiral, a triarylamine type hole conductor. And so, yeah, and so otherwise there's the same architecture. And so the hole conductor replaced electrolyte, you have a solid state cell. And so that was used to develop the present version of the perovskite solar cell. And if you look into Professor Sok's recent science paper, still, I mean, this is almost the same configuration we published. And Henry Snaith, he published, he's a former postdoc, he published almost same time. And it was, but it wasn't exactly the same. So we didn't copy each other. He had used aluminum oxide to support the perovskite. And so, yeah, so these were the two papers, the first solid state. But I have to say there was also the Kanatsidis paper. It was also a solid state. But he used the perovskite as a hole conductor. So instead of the spiral, and he could see that the hole conductor also increased the visible response. If you look at his paper, you can clearly see it was published in Nature. And so, yeah, and that's this. These three papers were the basis in 2012. Okay, there were some other publications, but these are the key papers that that launched the the increase in publication. See here, 2012, we had one paper from Miyazaki, the liquid cell, and one in 2011 from Namgyu Park. But then it really took off as a solid state. And see here the number of papers and also the efficiency. Efficiency now at 25.2%, still rising, okay. And but let me just point out to you, these systems are complex. It's not like silicon, you have one type of atom and can't do much about the electronic structure. So these are highly complex systems. You can change the anion, you can change the so-called B cation, lead, tin, or germanium being used, but there are other B cations. They just are not as colorful as the ones we are using for photovoltaics. And so the A cation is the charge compensating sitting in this cavity. And so the cavity is just the right size for cesium, formamidinium, methylammonium, and also guanidinium. But then, as I said, the conductivity is mixed ionic electronic. So, and we have the complexity of structure, the so-called 2D or 3D systems, where we have the spacer layer introduced, and so that that produces a whole new option of materials that is still unfolding, and so you have two types, a rootless and proper type, where you have just one functional moiety that interacts with the octahedra. And here you have a bifunctional linker. It's called Dine-Jacobson type. But then, you know, you're always up for surprising things in the perovskites. And just mention the photo effect on ion conduction. That was totally unexpected and came out of the blue. Oops. And it was actually Joachim Meyer. We collaborated with him. He's a director at the Max Planck Institute in Stuttgart. And I'm actually an external member of the same Max Planck Institute. And so we had a long-term collaboration with him. And he discovered that the ionic conductivity of these cells, of these materials, went up 100 times, several hundred times under light. And that was quite a shock to the community. And so, so going back to the how these films are produced, well, there's the sequential route, which we published first. You first put the lead iodide, and then you convert it to perovskite with whatever iodide, cesium iodide, methylammonium iodide. So it's separating the two phases for the perovskite formation. But a lot of people use just single step, and this was our sequential deposition. First put the iodide down, then we expose it to, for example, methylammonium iodide and propanol, and that gave you the perovskite. It wasn't necessary to heat it; it formed immediately the black film. And so, but here's actually how these cells look, the cross section. So you have the conducting glass, and then you have it's hard to see, but there's the mesoscopic layer, and this is this part filled with the perovskite, and then there's a capping layer. And today's perovskites, the capping layer has really taken over, and so that capping layer thickness is 500 nanometer. So the mesoscopic layer doesn't have the predominant function anymore as light absorber, but it makes a good contact. It has a very high surface area contact, and it stabilizes also this contact. And so we also find that there was a light effect on this crystallization. That's something unusual, and we could get it into nature because nobody had seen it. Okay? And that's actually my graduate student, Amita Umadisinghu, who's now in Cambridge. She discovered that light effect. And she was invited to the Nobel laureate meeting in Lindau after her Nature paper. and gave a talk. Look how proud she is and self-assured. That's what we need, young people that are courageous, self-assured. And so, yeah, and then there's the anti-solvent method. The trouble, I mean, this is usually for laboratory cells, and I think the high efficiency cells, most of them, they use this method. But it's very hard to scale up. I don't think it can be used in production. So if you want a good cell, you might try that, but it's pretty complicated. You have to first have everything in one solvent, and then you spin it down, and then you trip the anti-solvent, and then you, I mean, you heat it, and that gives you the perovskite. But then I should give credit to our colleagues from MSU, and you see Professor Gudlin and Tarasov. They came up with a very, very elegant way. They just converted lead in one shot to the lead perovskite. You see the equation up here, lead, and how is that done? Well, with the ionic liquid, which is methyl ammonium triiodide. The iodide itself is a solid, but if you add iodine, you make the triiodide. And so the iodine oxidizes lead to lead 2, and then you have everything to make the perovskite. So that was very elegant strategy, and it was published first in Materials Horizons, but more recently the paper appeared in Nature Nanotechnology, which gives you really a gist on how these systems are produced. But you can see right away here the lead is a 60 nanometer thick film, and it turns into 500 nanometer thick lead perovskite. So the volume expansion is huge. And so, because the density is much lower for the methyl ammonium lead iodide than for lead. And so, but the films behave well, and the efficiencies, very reasonable value for efficiencies were obtained. And so today, for a while, there was starting with 2014, there was a big interest in multi-cations. And this interest is still there, mainly from the community that works on tandem cells with silicon. So I'll say a few words about these multi-cation cells. So we take credit with Professor Meyer again for having discovered that the formamidinium lead iodide which is not stable at room temperature. It forms a delta phase that is yellow and is useless for photovoltaics. So you have to go over 160 degrees to stabilize the alpha form, the desired black form. So that's a problem, and formamidinium is preferred over methyl ammonium because it's more stable, it doesn't decompose. And it has also, the lead iodide salt has better optoelectronic properties. And so then with this group, again, Norman Pellet was first, he discovered, I think he was jointly appointed by Stuttgart and our lab. And so we found that could stabilize the lead formamidinium by just adding a little bit of methyl ammonium, say 10%. And so you see what we say there. This concept has not been applied previously in perovskite-based solar cells. It shows great potential as a versatile tool to tune the structural, electrical, and optoelectric properties. And this has this statement has been verified by the last year's development, so it was a correct prediction. And you can also see here already the formamidinium itself is a mixture. Is a dashed line, shows much steeper response, goes further into the red. So as a single cell, you want to be as close as possible to the Shockley-Queisser limit in the light absorption. But that would be around 900 nanometer. So shifting towards this limit gives you a higher efficiency, at least the theoretical efficiency goes up. And so then the same thing happens when you add cesium to the formamidinium. And it's very striking because the cesium itself doesn't form a stable perovskite at room temperature. So it looks yellow. That's the yellow cesium that iodide film. Formamidinium doesn't, but just mixing those, you can take grind them together, they turn black. Okay, and so you see also Namgyu Park here, and he was one of the first ones to do that experiment, and we did some theory. We published about the same time, and we tried to understand why this was going on. And so just so you make you understand, if you look at the iodide series, the lead iodide series, so there is cesium, but you have to go over 590 Kelvin, okay? That's over 300 Celsius to get the desired alpha phase. This is a cubic phase. And for formamidinium, it's 163 degrees Celsius. So you have to be up there, then you get that phase. But at room temperature, it converts spontaneously to the yellow phase, which is useless. It doesn't have any light absorption, and you can't use it in photovoltaics. And but for methyl ammonium, you have the alpha and beta phase. That's tetragonal and cubic. They are very close, so they are stable. So that's why everybody uses methyl ammonium, okay? But in reality, people would like to use the inorganic one or the formamidinium, but you have to stabilize it somehow. For the bromides, it's not a problem, okay? You can see they all have a stable alpha phase. And so, at low temperature. And so the reason why this stabilization occurs, mainly the entropy of mixing is trivial. If you mix two cations, well, then you get entropy, and the disorder goes up, the entropy goes up, and it helps you. But it's not the whole story. It's also the fact that you need a smaller internal energy input to form the solid solution, okay? And so the two effects together, here you can see this is the combined stabilization effect. And again, this is published, and so we don't need to go into details. But that's a remarkable stabilization. And even today, to be honest, I mean, we still try to fully understand these phases, and some of them are metastable, they last for a long time. So still is a kind of an enigma. But then, I mean, there was a kind of inflation. We had three cations, cesium, triple cation, okay? So it's cesium, methyl ammonium formamidinium. And that paper was very well received and led to another paper with 4 cations. But then it stopped. We don't have a 5 because already there we found out that the rubidium doesn't really go on the cation side. It has benefits to put it, but still is kind of a riddle how exactly it works. Okay, so yeah, but if I now look at just maybe we fast forward, okay, fast forward science 2020, okay, and so here you see that this experiments from the Australian group I mentioned, and they passed this famous damp heat test and humidity freeze test. These are tough tests. For example, the damp heat test is usually 1,000 hours, 85 degrees, 85% humidity. It's like when you go in your sauna and you turn the temperature to 85 and humidity 85, and you stay in there for a month. Okay, how much would be left of your skin? And so this is a tough test, but there's another tough test, which is the operational stability test, where you have to run your cell over 1,000 hours at maximum power point at 60 degrees. So this test was not done in this paper, but I mean, this is already a very big achievement to pass that test. And if you look at what they used, I mean, I won't show the details of this paper, but trust me, they used a triple cation perovskite, okay? And they use the same meso TiO2 and arylamine whole conductor. So these ingredients have proved to be very, very rugged, and they withstand very strong stress conditions. And so stability is really an issue. And as I said, operational stability comes next. And so we had submitted this paper to Science, and where we changed the whole extraction layer. We didn't use the organic arylamine anymore, but copper thiocyanate. And then the editor was interested in the paper, sent it for refereeing, and then one of the referee came back and he said, well, they haven't shown the operational stability. I'm sure they have done the test, so asked them to put the data in. And we had done the tests, and we put the data in. It showed a 20% decline in 1,000 hours. And as I said, at 1,000 hours and 60 degree full light on it and maximum power point tracking. And so we thought 20% wasn't bad, but the referee didn't like it, and the editor rejected our paper and said, don't come back even if you solve that problem. But we did go back because we discovered something new, and so that's so we discovered that it sufficed to put some reduced graphene oxide film between the copper thiocyanate and the gold back contact to stabilize the performance. And you can see that here now we got really over 1,000 hours at 60 degrees maximum power point tracking. No change. If we don't have the graphene oxide, this thing declines very quickly. And this shows you also, I mean, these cells are really, compared to silicon, they're very thin. They use very little material. And I dare say maybe several hundred times less material than silicon. So the cost of these materials is very, very low. And given the fact that they can be applied from solution, they make it, they are a tough competition for silicon photovoltaics. I'm not the only, I mean, they're not there yet, but this thing is moving forward, and a lot of people working on it. I mentioned to you the 15,000 papers. And so here you see that structure, the perovskite, copper thiocyanate, and that made all the difference in the world. And why was that? Well, under light, you create a voltage across the cell at maximum power point. And under this, that voltage created a deterioration of the back contact between copper thiocyanate and gold. And that caused the degradation. It had nothing to do with the perovskite. Yeah, and let me just finish. Oh, I'm almost finished. Don't worry, it will not be too much longer. So I told you that really the field is moving towards more complex structures like these mixed 2D, 3D, okay? Here you have a so-called n equals 1. You have one 2-dimensional layer, and then one layer that's just 2-dimensional. And then here you, on the 2-dimensional, put one additional layer of octahedra. And so building up a 2D, 3D system. And actually, these are very interesting systems for optoelectronics. They have quantum wells, they have excitronic features. But we are focusing on, they also are strong light emitters. And so there's a lot of interest in these 2D systems. And so, yeah, so I'll say a few words. We worked on some new spacer cations. These are the cations that are separating these inorganic layers. And for example, adamantyl ammonium, that was so one new spacer layer we introduced, and this bifunctional spacer layer. And so, yeah, this is a fascinating new field. It's you can use all your organic chemistry to make new spacer layers and test. This is a very creative field. So here we have published those paper with Joanna Milic, who's Zeno Koboka. She's a supramolecular chemist and has helped us to design those new 2D materials. Yeah, and at the very end, I have to I want to mention some ongoing research on the former meridinium. This has been a continuous what should I say, goal of researchers in the field that don't use the tandem system. The tandem system, they need 1.7 EV band gap. Well, the pure formaldehyde doesn't give that band gap. It's much lower. It's at 1.5 approximately. And so, but if you use a single cell device, then you would go for formaldehyde, and it's also more stable. And so the question is, can we stabilize the formaldehyde without adding too much components that would deprive this material of its favorable properties? Okay. And so this has been an ongoing topic that is fascinating, and a lot of people are actually investigating this. And so we submitted a paper recently. You see that's a multi-author paper. I've never been on such a paper with so many authors, but you see my name is still, you can recognize. And so that was an amazing phenomenon that Haiju Lu, who's the first author, he worked on it. He discovered it, that you can produce these nearly pure. I mean, this is not the only, we are not the only ones that realize it is possible. And so with very little additive, you can stabilize the perovskite. But it's a complex story, okay? It's not just entropic stabilization, because if you add very little, then the entropy mixing will not be high enough. And so there's more to it. And that's a fascinating story. And so we have used a special heat treatment. These are the films. And it's just that they initially they gave between 23-24%, but our best cell is now over 25%. And you see also they are extremely highly luminescent, and that you need the luminescence. That's the check whether you have a good cell. If the cell has a low degree of radiationless recombination, you will get a high voltage back. And here, for example, the voltage is within, say, 120 or 150 millivolts of the radiative limit. There's a limit of the VOC, it's called the radiative limit. And so, so that's very close, and to the ideal case. We're not quite there yet, but getting up there. And so here's a famous equation that links the external quantum efficiency of luminescence to the voltage. And the ideal voltage, that's the radiative limit, which you can calculate. It's not so hard. And there's a paper by Ross who introduced it. We ourselves have published several papers. But at the end of the day, if you say, my cell is good and I have very few defects, then you should almost see with your naked eye the luminescence coming out. And by contrast, if you have a photovoltaic material that doesn't luminesce at all, then you have to worry. Then I would go down to low temperature, and if it still doesn't luminesce, throw it away. It will not be a good photovoltaic material. Okay, so so today we can make the black phase even at 100 degrees. That's 50 degrees below the phase transition temperature. So that's a heating with our new procedure, and this is heating without the procedure, the old procedure. And I mean, there's nothing magic about it. It's just that you stabilize. You have some kind of metastable system, because the alpha phase has a thermodynamic transition temperature of 157 degrees. Okay, and so if you're below that, you are by definition thermodynamically unstable. But what if you have a metastable state that can last for 100 years? Then you're okay for photovoltaics. Okay, so yeah, here's our best cell. And that brings me to the end. I have a lot of, I'd like to also especially thank the Global Energy Prize. I was a laureate. I was very, very fortunate to get this prize in 2017, and was very, very supportive for us. And so I'd like to thank our sponsors. This is our campus and some of our co-workers. And of course, in Switzerland, you have to go skiing. So this winter, this our group, I bought a magic pass where you can ski on many stations, but then, believe it or not, end of February, they all closed. Why was that? Well, you can guess. Okay. So with that, I like to thank you for sharing this evening with me, and I'd like to thank Alexei for his invitation again. Any questions are welcome. Thank you.